Bom, obrigado. So, good morning and afternoon, everyone. We're gonna start this video conference for the defense of Julia Carolina. She's gonna present us her work that she have been developing in the last years, and I would like to thank you all the members. And I am Marcelo Bianchi, the advisor, and I would like to thank Dr. Heiner King from Potsdam, and Dr. Carlos Vargas from Colombia, Professor Jorge Sanji from University of Brasilia, and Professor Marcelo Assunção from IAG.USP. Normally, we're gonna have a presentation from Carolina that should last for a maximum of 1 hour, but probably we are doing this by video conference. We can be like faster than that and more precise. And afterwards, we're gonna open for all the comments from all the members and the discussion. And so, thank you all for coming, and maybe Carolina can share the screen and to start the presentation.
So everybody can see the presentation?
Yeah.
Okay.
I think it's...
Good morning to anyone. Thank you for the evaluating committee for accepting to be part of to evaluate this work. I'm going to present the results of my PhD work entitled New Measurements of Crustal and Lithosphere Thickness for South American Platform using the Receiver Function method toward a 3D velocity model. This work has been developed mainly in the University of Sao Paulo and in the GEOFÍSICA laboratory of France. The presentation is structured in 5 chapters. The chapter 1 is a brief introduction. Chapter 2, 3, and 4 cover the most important topics of the thesis: a study of the 2 discontinuities, model discontinuity, and lithosphere-asthenosphere boundary lab. And the chapter 4, the 3D a priori velocity model. And finally, in chapter 5, the most important conclusions. So in the introduction, I'm going to briefly describe the 2 discontinuities study and make an overview of 3D velocity models in the area. So the first discontinuity study was the moho that separates the crust of the upper mantle and is characterized by a jump of velocity from 6.4 to 8.1 kilometers per second. The average continental crustal thickness is about 41 kilometers, given by Christensen and Monet in 1995. So the thickness varies according to the tectonic environment, being thicker in the orogens as Andes highlands and thinner in the rifts. In the South American, the last compilation was made by Assunção et al. In 2013. They compiled all the available works in the area, and the result was this model, this map. So due to the lack of the stations, there are some areas poorly sampled, and the resolution is not good as well. The lithosphere-asthenosphere boundary separates the outermost rigid and colder shell of the Earth, named lithosphere, from the ductile and weak asthenosphere. So there are different ways to define this discontinuity according to different properties: thermal, chemical, seismological, electrical. I'm going to focus in the seismological lab that varies between 70 kilometers and more than 100 kilometers in older areas as cratons. One of the most widely methods used to resolve the lab is the S-wave receiver function. So Kim et al. In 2012 compiled many works over the world that use this method to observe the lab. So we can see that in South America platform, there are a few measurements, mainly from Haidt et al. From 2007, due to the lack of the station also. So we have used new data of the area that has now many stations in order to better map this discontinuity in the South American platform. So knowing better the crustal and upper mantle structure allow us to construct better 3D velocity models that better predict the travel times of the rays and help us to better locate the hypocenters, which in turn permits to improve the tectonic studies, the seismic hardware studies also. There are many 3D velocity models in local and regional areas in the world, but in South America, there is no available 3D velocity model for a low area. Also, there is a global scale 3D velocity model, mainly known, namely the 3D RTT velocity model, regional seismic travel time. This model has a global scale, but only was refined in Eurasia and North Africa. So we tried to use this model in the South American platform in order to relocate a well-known Andean earthquake, the earthquake of Aikili in Bolivia. There is the red star. This is the weather epicenter. So these stars are the epicenters given by international agencies using 1D velocity models. And when we use the 3D RTT velocity models, we have a more accurate epicenters, but it's not close enough. There are distance about 20 kilometers. So due to the need to make a 3D velocity model, we have used the information obtained mainly in chapter 2 in order to elaborate a velocity model for the South American platform. So the study area is mainly the South American platform. That is the more stable and oldest part of the continental part of the South American plate. It is a result of the join of the Neoproterozoic cratons joined by full beds in a Brazilian Pan-African cycle. After the formation of the platform, most of the cratons and belts were covered by three large intercratonic basins, being the Amazon Basin, the Parana Basin, and the Parnaíba Basin. And there are also other two smaller but important basins. There are Pantanal Basin and the Chaco Parana Basin. The data used mainly in the two first chapters comes from the Brazilian Seismographic Network that formally started in 2099 by the join of 4 research groups of the University of Sao Paulo, University of Brasilia, National Observatory, and Federal University of Rio Grande do Norte. Until now, there are 95 broadband stations distributed in 4 subnets in Brazil. There are areas with higher density of stations like Northeast and Southeast. This data is free to anyone. And additionally, the University of Sao Paulo has been operating 38 temporary stations in the southwestern part of Brazil, parts of Bolivia, Paraguay, Uruguay, and Argentina. This data now is restricted by the research group. And with the installation and growth of the RSVR, now it's possible to detect earthquakes of magnitude 3.5 for Brazil, and in areas with higher density of station like Northeast and Southeast, the completeness is about 3 or lower of magnitude. In this figure, we can see that when the works mentioned of crustal thickness and the lab were made, there was in average 50 stations. So now when we updated these measurements, we have processed in average 150 stations. So is the main reason to improve this data with more stations. The coverage is better, we be better sampling areas and filling important gaps. I will start with the chapter 2, that is the updated model of the crustal thickness in the South American platform. We have used the P-WIB receiver function, that is a widely method based in the arrival of travel times of a PAS conversion in an interface, in this case the MOHO, and other multiples in order to estimate the crustal thickness and VPVR ratio. The data used comes from the RSVR and the temporary deployment data. And we have updated the crustal thickness map for South America. The results of this work were published in the journal GEOFÍSICA Research in 2019. And I'm going to present additional results from Peruvian and Bolivian stations. We have used almost 150 stations, mainly belongs to the RSVR, the temporary deployment also, and additionally 6 Peruvian stations and 1 Bolivian station. We have selected teleseismic events that are the blue circles, and also deep regional events, because have a more content of frequency and the resolution could be improved. The data were collected from 2015 to 2018. In total, we have processed almost 71,576 receiver function traces. In the pre-processing, for deep regional events, we have discarded the events that present a triplication of the P-wave according to the IAS 21 velocity model. That is this figure. And after we joined with the teleseismic events, and the data were detrained, tapered, filtered, and finally rotated to ZRT components. The receiver function traces were obtained by the convolution in time domain. And after that, the convolution, there were noisy traces that were discarded, selecting the better ones, considering that at least the PS phase were clearer. After that, we have a move-out correction to a reference slowness of 6.4 for each phase. After that, we have staked by phase also, and we have used a modified HK staking proposed by Hayt et al. In 2014 to estimate the crustal thickness and VPP radio. We have used a fixed VP of 6.4 kilometers per second and weights of 0.6, 0.2, and 0.2 for the PS conversion and other multiples. As we used the modified HK staking, we also compared these results with the results obtained with the traditional staking proposed by Su and Kanamori, and the results have a good correlation. The improve of use a modified HK staking is that the uncertainties estimated are lower. So we have used this method to do all our estimations. We have compared also our results with other works. This work of Albuquerque is from the Amazon area mainly. The values of crustal thickness have a reasonable correlation. And the VPV ratio is a lower correlation, but this parameter is more scattered and it's more difficult to stabilize. We compared also results with the result of Luz et al. In 2015. These results is mainly for the northeast part of Brazil, the Borborema province. The results correlates very well. Luz et al. Estimated a little thicker cross, but they used BP different, for example, and the BP rate also correlates well. We compared also with the results of Asunción in 2013, good correlation for crustal thickness, and other work that also shows a good fit. The results, I will present the map of crustal thickness and VPV radio. Each circle is the station processed, and the colors are the crustal thickness that varies to blue, the thinner one, to red, the thicker one. In the crustal thickness, the most important findings are the thin crust along the eastern edge of the Pantanal Basin, this area, that now is a thinner belt. Also, there is a normal to thick crust from the west part of the basin. And we have found a normal to thin crust in the Chaco-Paraná basin that are significantly different for the crustal thickness in the Paraná basin. That there are values more thinner in the limits. For the VPV ratio, is the first time that this parameter has been mapped in a large scale in the area. So the results are more scattered, but there are important patterns, as the low radius lower than 1.74 in the eastern part of the Pantanal Basin, that is the narrower belt of thin crust in this area. In the Paraná Basin, the values obtained are between the expected, but there are higher values in located areas, different to the northern part of the basin. And in cratonic areas as the San Francisco and the Central Brazilian Shelf, we have found normal to low values that are expected for the craton, that indicating a felsic composition. As we also use the original events, in most cases the results of crustal thickness and VPV ratio correlate well, being the values of VPV ratio more scattered, and uncertainties of the original events are greater because there are less data. So the most important thing of the processing these kind of events is that we have a better, in noise stations, it's possible to have a better, the different events that are high frequency content, and it's possible to estimate a crustal thickness with these events. For example, in this station with teleseismic data, the receiver function don't show a big conversion in the time expected of 5 seconds. So with deep events, this conversion is clear at 6 seconds approximately, even with less quantity of data. So there are stations that where with teleseismic data were not possible to estimate the crustal thickness, but with the help of the deep events, we can estimate in these stations the crustal thickness and VPV ratio. So the most important thing or result is the updated crustal thickness map in the South American platform. This is the previous model by Asunción et al. In 2013, and this is our updated model. The most important differences between two are the along north-south belt of normal to thick crust from the central of the Amazon craton to the southern section of the Paraná Basin. Also, there is a belt of thin crust in the sub-Andean region that is narrower than in the previous model. And the eastern part of the Amazon craton appears to have a thinner crust than the western part of the craton. We have processed also additional data from Peruvian and one Bolivian station that are the squares in the maps. The Peruvian stations are located mainly in the sub-Andean region, and the Bolivian station is located in the central Brazilian shelf, and the adjacent stations are from the temporary deployment that have less quantity of data, and this station helped us to confirm the results obtained from that stations. From the stations in the sub-Andean and Andean region, due to the complexity of the area, the traces were noises, but we have estimate a thicker crust in the Andean, thicker than 45 kilometers. That is the expected. And for the Amazon part, in the sub-Andean region, we have found a thinner crust, a slightly thinner crust compared with the station of the basin. And the Bolivia station is currently with other stations. And the BPV ratio in the Amazon basin are high, as expected, because the thickness layer of low velocities. And the Bolivian station are different, but this parameter is, how I said, is more difficult to stabilize. So now I'm going to present the results of the lithosphere ionosphere boundary under Brazil. I have used the S-wave reservoir function with the RSBR and temporary the station data in order to estimate the lab depth under South American platform, mainly Brazil. So this method is very used to resolve mantle discontinuities and has very advantages as the SP conversion does not interfere with the crustal multiplex because arrives before the S-wave train, and is more suitable for gradual transitions as the lab in mantelic depths, but also has disadvantages as these traces tend to be noisier than the traces of P-wave reservoir function. It's not possible to resolve fine crustal structures due to the content of frequencies. And for the South America part, there are a smaller number of available events compared with other areas. It's about 25 events per year. Compared with other areas, for example, in Europe, there are in average 100 of available events. So the data used are the permanent station of the RSBR. Also, I used the temporary stations, and we processed 4 international stations in the area in order to compare with previous results. The events selected are teleseismic events between 75 to 85 degrees. The data were collected from 2010 to 2020. We have processed in average 20,000 of reservoir function traces. The processing first, I rotated the seismograms to the coordinate system LKT, and after the convolution, the time and amplitude were reverted in order to have the SP conversion before the time 0. And we have selected the good traces visually And after the selection of these traces, the stations that belong to the RSVR have more than 150 good traces by station, while the temporary deployment only has 60 good traces by station. After the convolution, we have made a move-out correction to a reference slowness also of 6.4, and we have stacking the traces using a bootstrapping 100 times in order to estimate uncertainties. We have tried 5 different frequencies, low-pass filters. So we have selected that time were converted to depth using a IAG.USP model. And after that, we have compared the results of the model. So with the SY receiver function, it's possible to estimate a model that is the positive arrival. So we have estimated the model in all of these frequencies, and we compared the results with those obtained in the chapter 2, and we found that the better correlation is with when we used a low pass filters of 6 seconds, and we have used this filter to obtain our lab measurements. The results, this map shows the lab depth in each station processed. The size of the circle are the uncertainties. When the circle is greater, the uncertainty is lower. And for the smaller circles, the uncertainty is greater. In general terms, we can see that in the cratonic areas, the lab is thicker, and in younger areas or full belt regions, the lab is thinner. The Amazon Craton, for example, has a lithosphere up to 200 kilometers. We also confirmed a thinner lithosphere in the Borborema province, proposed by Hayes et al. In 2007. Also, there is a thinner lithosphere in the ocean continental margin. The San Francisco Craton presents also a thicker lithosphere, and in the borders, we observed a thinner lithosphere of 100 kilometers approximately. In the Paraná Basin, or in the area of the Paraná, Pantanal, and Chaco Basin, the measurements are more scattered, but an important feature is the thicker lithosphere in the southeastern part, and in the Paranapanema block, that is a cratonic block proposed in this area. So I'm going to show the results by each area in order to detail some important findings. In the full belts, unlike a Borborema province and Mantiqueira province, the lab varies between 70 to 100 kilometers. In general terms, the negative arrival that marks the lab is very clear. Only in the Borborema province, in the inland stations, I found a thicker lithosphere. And in the Mantiqueira province, the thicker lithosphere is found near to the border with the San Francisco Craton, where it's expected that the lithosphere is thickening. So in the cratonic area, the lab varies between 100 to 200 kilometers. So in these sections, we have found 2 negative arrivals. The first one was interpreted as a mid-lithospheric discontinuity, also found in other cratonic areas in the world. And the second one was interpreted as the lithosphere-stenosphere boundary. So the MLD appears to exist in all traces of the cratonic areas. Even if it's a weak arrival, its conversion is in the receiver function traces, and has depth of 90 kilometers. In the area of the Paraná, Pantanal, and Chaco-Paraná basin, there are we also found MLD, that is a mid-lithospheric discontinuity, in some traces, but other traces do not present two negative arrivals. So when there is there are two negative arrivals, the first one was interpreted as the as the MLD, and the second one as the lab. And when there is only one negative arrival, was interpreted as the lab. So in this area, most of the stations belong to the temporary deployment that has a less quantity of data. So in order to confirm our results, we have staked the traces in with other approach, that is the piercing point. We have divided the area in boxes and stacked the traces inside these boxes. And we also observed sections with two negative arrivals. These maps shows the results of two approaches of staking. The most characteristic are conserved. In the map with staking with piercing points, the circles are considering only the first arrival, and the squares considering the second arrival if it exists. And we can see that for the southern part of the Amazon Craton, also there is two arrivals and showing a thicker lap. So the most important difference is that at the south of the Paranapanema block, when we're staking by piercing point, looks to miss the second conversion, being the lithosphere in this area more uniform. So we have compared our lab measurements with the seismicity reported in the area, discussed by Bianchi et al. In 2018. And we have found that in areas with thinner lithosphere present higher seismicity, like the Borborema province, for example, that is the northeast Brazil, the Ocean continental margin, and also the eastern part of the Pantanal basin that present a thinner crust and lithosphere. In the Amazon Craton, in general terms, do not show a higher seismicity close to the station analyzed. The seismicity of this area is related to the subduction of the Nazca plate. And in this area is observed also seismicity, and we have estimated a thinner lithosphere also. We have compared also our data with heat flow data of the area. In general terms, areas with greater heat flow has a thinner lithosphere, and cratonic and colder areas present a deeper lap. So we have additional to the manual readings, we have prepared a second set of automatic measurements with the objective of not being biased by the interpreter. And we have correlated this data with the heat flow data, considering lithosphere thickness thinner than 130 kilometers. That this data tends to present a linear correlation. And the results, the residual of this fitting tend to have a normal distribution that indicates that the errors are non-systematic errors. The brown diamonds in this part are the manual different lectures. That is when a manual interpretation was made, we have found two arrivals, and the automatic set calculated the lab thinner. So the most important thing of this part is that the second arrival only appears to exist when the heat flow is lower than 75 watts per meter square. that are the colder areas. And for areas from higher heat flow, this second arrival appeared to miss. So in base of the results, we propose that the heat flows change the velocity structure of the upper mantle, making impossible to detect the lab but the S-wave receiver function in areas with higher heat flow. And in areas with lower heat flow, the lab conversion appears even weakly, but appears, and the MLD appears in the two cases. So our results indicate that the lab is present in cratonic areas, and the MLD is present in the cratonic and younger areas. So the S-wave receiver function or using this method is not possible to distinguish if we are resolving the MLD or the lab, or if we are mixing these two discontinuities in the maps presented, or we have to separate between MLD and lab. So more geophysical studies need to be made to define this point. And finally, I'm going to present a 3D a priori velocity model from South American platform. This final chapter was worked in the GEOFÍSICA laboratory in France under the supervision of the researcher Yvonne Font. We have constructed a model that captured the most important heterogeneities in the cross and upper mantle. We have used mainly the result of crustal thickness from chapter 2 and other regional and global data. Considering the seismicity of the South American platform, mainly Brazil, and also the Andean seismicity, the superficial seismicity, we have defined the area lighted by the blue square to elaborate our models that include the seismicity reported and the stations of the Brazilian seismographic network, both temporary and permanent, and also some international stations. So to the construction of our model, we have used considered three discontinuities: the topography, the sediment basement, and the mode depth obtained from chapter 2, and crustal and mantle velocities. Unfortunately, the local and regional P and S-wave velocity models don't have the resolution enough to use in this work as the time that this model was made. So we have used other available global and regional data. The structural data comes from the topo model by the NOAA, the crustal the sediment basement is from the crust model, the crust 1 model, and the mode depth is from the results of chapter 2. The velocities comes from the compilation from the global literature, given preference to active seismic experiments data. For the sedimentary velocity law, unfortunately, we didn't find regional or local data, so we compiled the global data from other basins like Los Angeles, Bengali, bases in Italy. We have averaged these data, and after we have made a polynomial regression of this average in order to obtain a relation of the velocity with the depth, showing in this figure. The predicted velocity law obtained by the polynomial regression is the red curve. For the velocity law for the platform, was the methodology were the same. So in this case, we have used some data of the northern of Brazil, but also considered global data and the average given by Christensen and Monet. We have averaged the data and made a polynomial regression to fit these values. And finally, we have constructed another velocity law for the Andean part because the velocity structure are different. And comparing the crustal velocity law for platform and for Andean region, can see that for same depth, the velocity in the Andean region is lower than from platform. In all these cases, we ensure that the bottom of the velocity of the sediments in this case is lower than the velocity of the top of the crust. And for mantle depths, we have used LNL velocity model that is a global 3D velocity model. This model was made by Simmons in 2012, has a resolution of 1 degree and is consistent with the position of the Nazca plate. In this case, the lowest mantle velocity is 7.8 kilometers per second. That is higher than the velocity of the bottom in the crust part. This jump of velocity ensuring a consistent velocity jump mode discontinuity. So in order to know how to be our model, we calculated the theoretical rate paths according to the IASP 21 velocity model, and we can see that for events in a regional distance up to 30 degrees, the rays don't go deeper than 800, 900 kilometers deep. So our vertical extent is from 7 kilometers above the sea level to 900 kilometers depth. It has a horizontal resolution of 0.5 degrees, and the vertical resolution varies with the structure. Up to 10 kilometers, there's mainly sediments, 1 kilometer. In crustal depths is 2 kilometers, and in mantle depths is 5 kilometers because the velocity gradient is lower. So this figure represents our total volume of the area to construct the model. We have the sediment basement, the model depth, and in this case, the Nazca slab. So we have divided this volume in cubes. There is a sum of that cube, and each red edge represents the average velocity of the surrounded below, given by slowness. So our total volume was divided in these cubes, and as our model begins at 7 kilometers above the sea level, there are areas that there is only air. These nodes were filled with a velocity of 0.3 kilometers per second, and when the topography relief begins, each node is filled with a velocity information of the corresponding structure, sediments or crystalline crust. When a discontinuity is found, the average velocity, we average the velocity loss of the two types of structure, and the velocity crust of the platform and Andean crust were weighted average, considering the distance of the node to the limit. In the central axis of the Andean part, we have used a Andean crust as totally, and as well as the node is distancing of this point, the two types of velocity loss were averaged, considering the distance. Our results of our model shows a clear difference in velocity between structures, sediments, crust, and mantle, according to the structural data, and reflects the real geologic and environment of our area. For example, in this vertical cross section, the mode depth is well defined, and there is a consistent velocity jumps in the crust and the mantle, and this part that is the Andean region, and this is the platform. We cannot see high contrast of lateral velocities in a transition from Andean region to platform. And also, looking the horizontal cross sections, there is a lateral variation important, for example, in this part at 4 kilometers depth, when most of the continental part present crustal velocities, but we can see the Parana basin that has a average of 5 kilometers of sediments. For deep of 35 kilometers, we also can see crustal velocities in the main part, but some areas that presenting crust as the sub-Andean region begins to have a velocity mantle, begins to have mantelic velocities. So in order to test our model, we relocated the Aikili earthquake that I mentioned in introduction. We have used 14 stations. Most of them are to the west of the event. We have used the non-link log routine. And this figure shows our first results. We can see larger uncertainty to the east because the gap of the stations. As the closest station is about 400 kilometers and a low quantity of P-wave arrivals, the uncertainties are higher than expected, about 20 kilometers. But the residual are less than 1 second, is 0.53 seconds. The stations show residue from less than 1 second and almost 1 second. It's a good residual because in general terms, the stations in the Andean region presents greater residue. Generally, when you use 1D velocity models. So comparing the epicenters obtained with the non-link log, there are the blue and green stars. They are the most closer to the better epicenter given by Fanning et al. This epicenter was obtained using INSAR methodology. The more away epicenters are given by international agencies that use 1D velocity models. Trying with the 3D global velocity model not tested in South America, these epicenters were obtained. And using a 3D velocity model elaborated with local and regional structural data, we have obtained the epicenters with a better accuracy to the other ones. We also tried to relocate other platform events with this model. One of these events are Amargosa Earthquake, occurred in the Bahia state in the northeast Brazil. That is almost the ocean continental margin. This event has a magnitude of 4.2. Many aftershocks were relocated using a local network of the Federal University of Rio Grande do Norte. This figure shows the results obtained using our model and the nonlinear load routine. The blue and green stars are the PDF and expected epicenters given by the program used. The red stars are the epicenters located by the local network. This are aftershocks where has uncertainty less than 200 meters. The orange one is the epicenter given using a hypo 71, and the 1D velocity model used in Brazil to tries to mimic the travel time of a 3D velocity model. So our results are consistent. The better epicenters are inside the ellipse of error. And also, we tried to relocate the Guyana earthquake. This earthquake occurred in the January of this year. It's the largest earthquake in the South American platform, recorded by the Brazilian Seismographic Network. The better epicenter, that is the red star in this part, is given by INSAR location also. We have used 10 stations in order to relocate this event. So our results also are close to the real epicenter. So in this case, we have a great uncertainty to the south-north, because to the north of the event, we don't use any station because this is the limit of our model. So in general terms, the real epicenter is inside the ellipsoid. This is the epicenter given by the satellite. The purple star is the epicenter given by the catalog of the University of Sao Paulo, obtained with 1D velocity model. So our model shows a consistency in velocity and shows that works in the epicenter location. Finally, the most important remarks. For the crustal thickness in the South American platform, we have updated the model in the area, improving the resolution in areas of the Amazon crater and the sub-Andean part. The average crustal thickness of our observation is 40.1 kilometers, close to the worldwide average for platforms given by Christensen and Mooney. And also, we mapped the VPBS radio by the first time in the South American platform. Talking about the lithosphere asthenosphere boundary in Brazil, the lab depth varies from 100 to, in the fault belts regions, to 180 kilometers in the cratonic areas. Also, in cratonic and colder areas, we have observed two negative arrivals, interpreting the first one as the MLG and the second one as the lab. And we found a good correlation between high intraplate seismicity with regions of thinner lithosphere. And for the 3D velocity model, we have elaborated a model that shows a realistic velocity variation with the most important interfaces, sediment basement and mode depth, as well as shows a lateral velocity variation according to structural data also. Using our 3D velocity model, we have successfully relocated a well-known earthquake, as well as the other two earthquakes in the South American platform. And the way that model was constructed allows us to update when accurate seismic and seismological studies are available as regional or local P or east wave velocity models. So thank you for your attention.
Thank you, Carolina, for the presentation. I think we are inside the proposed time, and I would like to ask all the members if do we need time and 2 minutes for going to bathroom or even drinking some water, and also if Carolina needs time, please you just tell me and we make a break in the process.
Now for me it's okay.
Okay.
2 minutes? Just to go to the bathroom.
Okay.
Okay.
Okay, so now we can make a pause for some minutes, some 3 minutes, so that everybody can drink water, go to bathroom, and we come back to start the arguation.
Thank you.
No problem. Just let me know. The connection was good to everyone?
For me, it's okay. Yeah.
Yeah, very good, Carlos.
Eu vou pegar um cafezinho.
I think everyone is back. I saw. Ready. Okay, so I think we can start again. Everybody with the cups of coffee filled and So as traditional, I think we normally in Brazil we start with the most distant member of the committee. So if everybody's agree, I would like to invite Rainer King to make his questions and comments about the work to Carolina, if everything is okay. So you can start, Rainer, please. Be welcome.
Okay, yeah, I can do that. Well, I think, Julia, this was a great deal of work, very substantial work in many different fields that looked very, very good. What you did. I have a question about the more depth. You used P and S receiver functions. You have mentioned that. Also,
Sorry?
You used P receiver functions and S receiver functions.
Yeah.
You mentioned S receiver functions, but you didn't show any figures. But in your dissertation, you have compared. You have a figure comparing more depths determined using P receiver functions and S receiver functions.
Yeah.
And the results looked very, very embarrassing, I would say. not very linear comparison.
Okay.
So what is your conclusion from that? You apparently used only the P receiver functions and disregarded the S receiver functions.
Sorry, Rainer, I can hear you very well.
You used only P receiver functions, not S receiver functions in your results, in the continuation of your dissertation.
Yeah.
Why is that? And what is your conclusion from the lack of agreement between the two techniques?
Yeah, we have used S-wave receiver function in order to resolve the lab. We measurement also the more depth with this technique, but the purpose of this comparison was to know what filter is better to use. I don't know if you are looking the.
I see your figure. Yes, I see.
The figure. I not presented that by that time because it was a short time to present all the work, okay. But. These figures are the comparisons. For the S-wave receiver function is more difficult, I think, for the MO, for example, to have a good accuracy, because with SRF we use it only one arrival, and with the P-wave receiver function we use the PS and the other multiples. So if we see the correlations using both approach are using the low pass filter of 6 seconds is a consistent result, but I think that S-wave receiver function is more suitable for lab or other mantle discontinuities, and the P-wave receiver function shows a good power, a very powerful technique to resolve the mode depth, because uses many the principal conversion and other multiples.
Well, it's certainly right. The P receiver functions are much more frequently used than S receiver functions. So it's just a continuation of the work what most people are doing.
Yeah.
But I don't agree that the S receiver function signals are bad. I mean, the signal noise ratio of S receiver functions for the MO is usually much better than for P receiver functions. And also the periods are longer, but if you measure the time looking at the maximum, the depth accuracy of reading the delay times is not that much worse. And in P receiver functions, you showed a few examples. Usually the multiples are very poor. And if you look at the Sul-Americana diagrams, you use the maximum of this diagrams to determine agent K, But the maximum is not clear defined. It's usually very broad regions. This is an indication that the multiples are poor, usually. So I'm not really convinced that that is the best solution. You have just going ahead with what the majority of the people are doing. If you look at this figure, which is on the screen, I think it's really difficult to make a decision which one of the two more depth determinations is better than the other one.
Yeah, for example, when we use a low-pass filter of 2 or 3 seconds, the measurements are more scattered. In this, sorry, I'm not presenting, I think. It's more scattered in this part. Are you looking my display?
Yes, I see that.
Okay. In this figure, the measurements are more scattered with these filters. Also for 4, 6, and 8 second low-pass filter, the measurement tends to be more, to have a better correlation. So with 6 seconds, I think it's a less variation. There are problems also with the S-wave receiver function appears to estimate a lab depth thicker than the P-wave receiver function. But one disadvantage of the SRF for South America is the available of the data. There is a few traces by the geological position also. So I think it's
But you have certainly less S-zero functions, but your S-zero function data, especially the Moore signals, look very good, I think. And in my opinion, we wouldn't even need to filter. Broadband data are maybe better. They keep all the periods, don't filter out anyone, and you see short and long periods in the same trace. I would have preferred that. Of course, I don't want to insist on too much.
No, I think it will be interesting to do a future work comparing these two techniques, and with more data of SRF, validate, compare with the data that we have with P-wave receiver function. There are many works using this method in the area that can be compared.
Yeah, I think that you are right. That's certainly a good idea to try to use that method in the future as well, and to compare the results and see which ones are maybe more reasonable than the other ones.
Yeah, and when increasing of the stations is better, I don't know, in 1-2 years there will be more data available. I think it's an interesting work to do.
Okay, good. Maybe I have another question. You determined velocity depth functions for your final models. You used all kinds of information outside your direct data, but of course there are also possibilities to invert P-receiver functions. This is also quite frequently done, to invert the amplitudes, the signal forms and amplitudes of the P-receiver functions into velocity depth models.
Yes,
I'm not really very much in favor of this method. It's frequently used as well, and it's not really a very unique method. But I think it could set some boundaries. And perhaps I would also suggest to use that method as well, at least in comparison with the methods we have really applied. Did you consider using this method? Did you on purpose not use it, or what was the reason why you didn't use it?
Sorry, but I'm hearing with a noise. I don't know if only me that are hearing with a noise.
Okay. Well, I would like to know if you considered using the inversion techniques, the technique to invert the waveforms, the amplitudes of the P receiver functions, or if you just didn't consider it.
No, we don't consider it in this work to do that. We only in the chapter 2 estimated the crustal thickness with only P wave receiver function and the Sul-Americana modified method. And we used a fixed VP velocity, and also we tried to use the S wave velocity in each station given by a local model that I write in the document. So
my question was different. I mean, you can use the P wave signal, the waveforms, and invert that into a velocity depth model.
Okay,
without Sul-Americana
no.
I mean, you
No,
can
no,
do
no.
Sul-Americana in addition, of course, but this would be a method which provides for the entire crust velocity.
Okay, no, we don't consider in this work to do that, but I think we.
I mean, did you have any arguments against that method, or just
no? We didn't try to do really. Maybe in the future, other researcher could do that, but in this work we didn't try to do that. We only estimate crustal thickness as well and do not invert any waveform.
Maybe that would also be a good suggestion for future work.
Yeah. Always I think that the time is important to do many.
I understand that completely. Okay, so that's it for the time being. Maybe somebody else would like to ask a question.
Yeah, no, if you have more questions, Heiner, you feel free to do. Each of us can have like 30 to 40 minutes of questioning in blocks. So yeah, but you can feel free. If you have just this, it's okay. But if you like to do more questions or comments on points of your interest, you can do. There's no real issue or
you showed a figure where you used the P receiver functions. On one side there were all the traces, and the other side you had selected the best ones with some correlation method. I think you said so. How did you do that?
The correlation we have selected.
Can you show that figure?
Yeah, of course.
Can you display this figure? No, not this one.
Okay.
Probably this. Yeah, it's this one. Yeah. How did you do that?
I selected a good receiver function trace, considering that the PS were clearer and, if possible, the other two multiplies. And after I correlated this good trace with the other ones in a window of 20 seconds and retained the traces that presented a correlation higher than 76%, and the other traces were discarded.
Why only 20 seconds? I mean, the multiples take a longer time. The time delay.
Really, because when we consider a larger window, the returning traces were a less quantity, and in general terms, the multiples are not too strong to correlate, are in the level or noise sometimes, and we prefer to correlate the first conversion, the PS, that is about 5 seconds, and if possible, the second one, that is in areas with thin crust, is about 12, 30 seconds, but the phase that are most important for us was the PS, more clearly also. And for example, in the section that you're looking, the conversions are in the level of the noise, and a correlation with this amplitude doesn't work well.
I understand. I presumed that you used a long window which included the multiples, and in this case, it would probably be problematic. Would have been problematic for not considering a distance move out. But since you used only a short window, so this is it's completely okay. What you did. Okay, maybe another question. Besides Tsu and Kanamori, you used a technique by Ben Hyde also to determine H8 and K. I was participating in that work, but I don't remember exactly. Can you maybe most other people don't know it either. Can you explain that method again?
Okay, so in the traditional HK stacking proposed by Tsu and Kanamori stacked all traces. For example, if you have 20 traces, they stack these 20 traces and search the best fit to the crustal thickness and BPPS. For the modified method, we stacked we made a move out correction for each phase. So for PS, the PPPS, and the other one for the PPESS. And after we have stacked doing a bootstrapping of 2 times, each phases for each station. So as we have made bootstrapping 200 times, we have 200 traces stacked of PS, other 200 for the other multiple, and a third one for the PPSS.
Maybe you show the individual traces stacked, Carol.
Yeah.
Yeah, I understood that.
Yeah.
I understood that.
Yeah. For this example is this example shows the PS PS stack. This is the PPS stack and the final stack. And finally, instead to read that 3 times for one trace, we read each time in each trace. So we read the PS time for this stack.
For the summation trace, from summation trace.
Yeah, this is a stacked trace. This is another stacked trace, and we consider the arrival time of the PS of this trace, the PP is for this trace, and the PPSS for this trace, and uses the.
Yeah, I think that's there's maybe a better method even than the original Tsu and Kanamori, because here you can look at the multiple stacks and decide if it is a signal at all or if it is noise, and then pick the arrival time, and then you are sure that the multiples are there. But in the way the usual the ordinary Tsu and Kanamori method is used, usually multiples are very poor. In most cases, it's not very nice the way how it's used. So on which method did you rely more? This method or the original Tsu and Kanamori method?
I personally prefer the modified method because the stacked traces is a corrected traces for a reference slowness, and also this method shows lower uncertainties because when the traditional HK stacking, there is no move out before the stacked, and the signal can be destroyed by the different time arrivals.
Okay, I'm happy about that. Then maybe one more question about the LAB and MLD in the data you have shown. Can you show one of the examples once more, please? MLD and MLD.
Okay.
Some special one for
Yeah.
Creighton?
I don't recall exactly which one,
Okay.
but just
I
take it.
think it's that.
Here, yeah, I can see it. For example, in the left ones, you have two green marks in a number of cases.
Yeah.
Yeah, and well, isn't that a little bit optimistic to take, for example, in the left figure, the bottom green mark? I wouldn't think that there's anything.
Sorry?
If you look at the S receiver functions on the left part of the figure, you have two green marks for probably MLD and LAB. And the bottom one is probably LAB and the shallower one MLD.
Yeah.
But at least at the right part of the figure, the LAB signals are zero. I guess there's no signal. No real signal.
Yeah, it's a noise signal. So we try to select in this case, a lab that is consistent with nearby stations, and considering that it's a craton, that the bibliography reads show that these areas present a higher MLD phase, that's a higher signal than the LAB. So in the final, I think I told also that maybe we are misinterpreting the MLD where the lab is in the frontier of the S-wave receiver function. It's because this interpretation is a manual interpretation, is biased by the interpreter. So to do the correlation with a heat flow, we prepared a second set of measurements, automatic measurements that searched automatically where is the largest negative arrival between 0 to 20 seconds that is not biased by interpreter. So in both cases, there is a possibility that are interpreting the lab as the MLD or the inverse.
I'm not sure if this is a good way. I mean, you should make the decision if the LAB exists on the basis of that data and not looking at other data, completely different kind of data, and then going back, there's maybe something, so I'll take it. I mean, this is an important issue. There's a long discussion about the existence of the possibility, even the existence, but the possibility to observe the LAB in cratonic areas in 200 kilometers depth. There's a debate going on for that. And if you look at the left part of the figure, there you have some red signal. It's three traces. And this is very important. In this place, I don't know if it's geologically somewhat different or not. There you have an observation, which might be LAB. But at that depth, the other green marks should not be used, should not be marked there. There's nothing there.
Yeah. So, for example, for this section, we consider the first one as the lab and read the other negative arrival after this arrival of 10 seconds. That is very minimal, really. Or also could be this arrival, but it's a thicker one. So there is a decision of the interpreter what negative arrival choose to do that, to read as lab or MLD.
Well, I guess if you submitted this to a journal, the reviewers will cause problems with these arrivals.
Yeah.
Okay.
Further,
thank you very much.
thank you to you, kind.
Okay.
Thank you, Heine, for the comments. It's something that we are still working on, and it's great to have inputs for people that are really working on that. So I think we can move on to the next one. So I would like to invite Carlos for making some points and comments or questions to Carol.
Okay.
Thank you, Carlos. You're welcome.
Great. Thank you so much, Carolina. Very nice presentation.
Thank you.
Interesting contributions. So I just start to ask you about the anisotropy. I suspect this scatter pattern that you showed in the previous slide, when you compare the way cyber function with X-way cyber function.
Carlos, sorry, you can talk closer to the microphone, please?
Yes.
Because there is...
Could you move?
Just a minute, Carlos. Carol, can you close your microphone at the same time that Carlos is talking? I think this helps also.
Sure. Could you please show again the slide where you comparing the side functions between P and this way, please? This was 57, exactly. Yes. Okay, very well. I just suspect that maybe this scattered distribution of pattern corresponds to an anisotropy effect. What may you tell us about the anisotropy analysis? Why not incorporate into this part of the thesis? Yes, what can you tell us? Microphone is
off. Microphone is off too.
Okay, we didn't consider anisotropy measurements in this part of the work. There are anisotropy measurements in the area that could be added or help to interpret. So I think that a part of the anisotropy, when a low pass of 2, 3, or 4 seconds, a part of the signal there could be other lows that are, or the convolution residuals or noisy that can be misinterpreted. So could be interested to add anisotropy information in this part. I think that for the lithospheric boundary, anisotropy is an important parameter, as well as to better define or understand, for example, the MLD also. So I think it's a future step maybe for other researchers. In this case, the focus was where use the where cyber function and obtain a first version of lab depth in the South American platform, mainly Brazil. And with new data, it can be have a more complete vision of the area. I'm really not, I've never worked with anisotropy. I understand the basis of the anisotropy, but I think it's an important thing to understand all the mantle discontinuities and help to discuss and interpret our data also.
Okay, something that we need to move on this analysis. Yes, I think that Marcelo should move into this part, or maybe you, Carolina. Could you please go to the slide, the previous slide with the receiver functions, stacking automation. Maybe 55, please. Two previous slides. Yes. Yes. Once again, I think the analysis of the anisotropy could be an interesting contribution. In this case, for example, I see maybe the azimuthal distribution of the receiver functions. In this square, I can see much better. Yes, exactly, much better contrast in some waves. But we lost the main, well, the left, exactly, the left interpretation. So I think absolutely, for me, is an anisotropy issue that you need to move out. Basically, the azimuthal distribution could be incorporated in this sort of analysis, but you don't, your thesis, this is all, or maybe you want to move a little more, but it's not really complicated. And in this case, it could be very interesting contribution in addition. Any comment?
Really, so I didn't present this slide in the presentation because of time, really. So it's a thing that I wrote in the thesis, that there is appears to miss the PS conversion in the blue square. So I wrote in the thesis, I think that is an open question for the moment that I presented the work. So I didn't think in anisotropy at the time, but now it's like a window opening to explain this data, because it's a great question for me and the moment to interpret the section. It was the first thing that I thought was the slab of the plate in subduction, but doesn't fit with the depth of the plating at this position. And I was thinking, and so it's one more time, it's that time for, oh, okay, go on to finish the things. And it's a open question, and as I said, it's a window opening for me now to include anisotropy, to interpret this, because it's for me it's a very interesting result of this station, and it's a good station. It's not a noisy station, and there is a clear gap of PS arrival in this azimuthal window.
Yes, but not only in the lab, for the lab analysis, but also for the
this is the
exactly. Yeah. I see in this square actually the upper waves are also highlighted.
Yeah.
Probably is based on azimuthal effect. Okay, very well. Thank you so much for this issue. It could be interesting analysis. You should move in this analysis in the future. The other side, I just curious. For you, that you remember you put an analysis of heat flow with thickness of the lab, well, the depth of the lab. I'm not completely sure about the heat flow contribution of the astenosphere, or more specific contribution of the heat flow measurements in the surface is coming from the crust, basically because we have a radiogenic contribution. Of course, we have a granitic crust, we have more heat from this part. Question is then, why you now consider to contrast, to compare heat flow with the crust thickness? Why use only lab thickness?
Thank you, Carlos. Really, I didn't compare with crustal thickness because I don't think about that at the moment. this part, the crustal thickness, is a work that I made like 2 years ago, really. And the lab is a recent work, so it would be interesting compare. I'm thinking about that also because I realized that in general terms, the areas that have thinner lithosphere also has thinner crust. And I think that comparing the heat flow with the crustal thickness would be a good addition of the work. Add important and interesting discussion also for our results, and maybe to do more correlation with the geological setting of the area. I think I can do. I have to present a corrected version. I think that it's a good point to add to the discussion of the chapter 2.
Okay, very good. I want to see the results, please. Both the previous analysis of anisotropy, if you want, of course. Maybe this analysis could be interesting. Marcelo is a little happy with this.
No, I like the contributions, Carlos, because it's really, I don't know, for me, a PhD work is something that you work, and just in the end, you need to sum up and feel. So thank you for the contributions. I'm happy to hear this.
Okay, so in this idea, I don't want to overload with work, Carolina, just ideas, just consider, that's all. Another idea is about, I don't remember, 2-3 years ago, one of my PhD students published a paper about the Curie point depth in South America. I also wonder about why not consider to compare Curie depth point with this thickness. Once again, I think the contribution of the heat flow is coming of the radiogenic, in general, radiogenic heat generation. But when we compare the Curie point depth, is more about the lithospheric structure. Could be, I think it has sense if we compare this sort of thickness with the Curie depth, the Curie temperature. This is something that we can support you. We can send you our estimations. Maybe you can. It's a very easy exercise. This comparison is up to you. Up to you. If you want to finish this part. Any comment?
Thank you, Carlos. Really, it will be a good comparison. I didn't know that word you mentioned it, really. So I think could bring other point of view of heat flow or query of the lab. Really, as I mentioned it's a question also for us to correlate some other geophysical parameters with the lab and to constrain also results and distinguish or know where is the lab or is the MLD. Also the MLD, the origin is discussed until now by the researchers in the world, and with the amount of data that we have, it will be interesting. Thank you to you to give us that ideas.
A final comment is regarding about the BPBS ratio. I checked your thesis and it could be interesting, your comments about these distributions, but what's about the high values of BPBS ratio? All those about 1.8. What can you interpret? In particular, because many of them are used in the western part of your study area. What can tell us about these high values?
So in the Parana Basin, that is this area, there are some high values that are related to underplating or mafic processes in the area in the past. So in this area that are the squares that has high values, first we constrain our results with the range given by Christensen in 1925, 26, I don't remember the exact data. So this station also belong to the temporary deployment, has a low quantity of data, and this area is a very percent noise data. There is a basin, and the results are not good as well as we want. So maybe it's these high values is due a noise in the traces, or is reflecting the sediment layer of the area because it's a sediment basin.
Perhaps it's the sedimentary effect, that's right. Other idea is that if we consider anisotropy, also these values are just moving a little higher, depending if you are moving near to the orogenic areas, because these areas has high anisotropy. So this is partially an effect of the anisotropy. Anyhow, up to you. You check, think about, maybe you can rewrite some paragraphs. Thank you so much. Very nice work. Once again, interesting contributions. I'm happy for you. Probably tonight you are going to sleep very well. Bye.
Muchas gracias, Carlos. Thank you so much for the contribution, for the comments. Really, the overview and point of view out of the group, of the research, in this case, me and my advisor, the person that I always talk, is important, because when we are working a topic, sometimes you don't go outside of the comfort on the things you know, and I think it's important. For example, the anisotropy in all the results can help us to better discuss and understand the data observed. Thank you.
Thank you, Carlos. It was all ideas are very good and nice to improve the discussions. So our next participant is George. I would like to welcome George for pointing the contributions in Carolina works and expanding the discussion. You're welcome, George.
Thank you. Thank you for this invitation. After a long time, I'm back to participate of the TESE like this. I'm so happy and a little nervous because if you have some problem try to speak in English, it's not so good. You can skip. It's not so clear. I try to skip to Portuguese and try to talk and someone translate. Okay. I want to talk about for the reference Anisotropy errors. I will send all my appointments after that. Okay. Carolina, your thesis has a very wonderful results and very clear for me. I learned so much when I was reading your thesis. So you work hard. Then congratulations for you and the vice for excellent job. And so I'm so happy for this job. It's nice for our country, for our people, because we need to increase it for all nations, Peru and Brazil, about research. I love it for this, the international contribution, work together with French, and you have a nice team in USP to get a nice job, okay? Let's go. I have a first question for this job. You don't see tangential receive functions, okay? Because almost zero. So why you believe that the receive function tangential in time domain can help for noise or deep, something like that for your job?
Thank you, George, for the appreciation of the work. So I think that the convolution in time domain help us to better estimate crustal thickness and BPP rating mainly in noisy data. Really, I didn't try to use the frequency domain. So with the time domain, we have the advantage that there is no frequency content missing, and is one of the reasons that we selected this approach, and also for the noisy data mainly in the basins and the temporary deployment, and many other works of many years ago and until now are showing that for this kind of data, the time domain is maybe a better approach, but I didn't try the other approach of frequency domain, but comparing the results with other data, they correlate well. So I think it's better for noisy stations.
Okay. Could you please show the trace receive filtration for both of station? I think the figure 2.3a, but you show in the presentation.
Is this future?
Yeah, yes, okay. Just to have a doubt of this because you have on the left and the azimuth to sort by azimuth, yes? And the right, you have for the trace reference trace?
Sorry?
For the sort, for the
no,
order.
Is of the right parameter.
Right parameter, but yeah. This zero is this 6 point what? The zero is a reference for the base or the mid of this? You know my question? No.
And I don't understand your question really.
Yeah. I try to understand the trace because not distance is a reference.
No.
Okay. But my question is did the reference stay where? And the 0?
Okay. Now this 0 is the number of traces, and they're sorted by P parameter that goes to 0.5 to 0.8. It doesn't look in the future. Mine is sorted in this by this parameter. This number is the number of traces. The distance are 30 degrees to 90 degrees are sorted by the P parameter really.
Okay.
Maybe if you want to ask in Portuguese, I can translate, George.
Yeah.
Or could be in Portuguese if you prefer.
Yeah, okay, try to one more time português. Não, first time português. Porque eu estou perguntando se a referência desse traço, que é o traço que você fez depois que desenvolveu, depois que você pegou os traços melhores, se é o 0 é a referência ou é o meio dele, porque eu estou vendo também que tem um ajustezinho aqui na figura do lado, né? E se é a referência, se o 0 qual é a referência do traço de referência, onde é que ele está? Ele está no meio ou é do 0? Só para que eu entendesse. E na sua legenda não tem isso, né? Não tem falando que está azimuth ou se está na referência. Só para uma dúvida sobre isso. Será que está claro?
What is the reference trace you use it? Which is the one, the 0 or the last or the middle? Or that's the question. I think.
Yeah, really the reference traces I didn't highlight it in the section. It's not the 0; it's in the middle of the section. But obviously, I don't know what is the reference trace by the future, but it's not highlighted or it's not shown in any part. It's a trace with a PS arrival clear, so it's not highlighted in any part really.
Okay, it's good to put in the legenda for this part because you see the right and the azimuth in the left is the difference. It's not the same.
Yeah.
Oh, you put the same because it's good to see the difference of the two pictures by azimuth all the way. It's my suggestion. Did you show the HK stack in the presentation? Did you show? You can see but you showed in your thesis 2 pictures for good stations and noisy station, or good station and regular station, yes?
Yeah.
Okay, go ahead.
Yeah, maybe open the thesis.
Figure 2.7, you put this, and for me, it's just a question because do you have a noise station and homogeneous station on the why to say good and regular? Because maybe you have heterogeneity, the cross is not homogeneous, and you have 3 or 4 the minimums for to get a crustal thickness and the VP-VS ratio. Why you put the good and the regular?
The good station are that station that present only one maximum peak of the HK staking, like in the feature is showed by the black point.
Yeah.
So in some noisy stations, the HK don't converge to one maximum, so it could be 2 or 3 maximum, and it's need to do a zoom in the grid. And in order to constrain these different maximum peaks, we base it in the work of Christensen of 1996 that gives the range of values that in the cross and word can be adopted by VP-VP ratio. So for example, if the HK is taking in a noise station converge to a result of VPVS of 1.85, for example, is too high to be realistic to the Earth, and we selected other value according to the values of the average studies, and we selected this station as regular station because there are several maximum peaks.
Yeah, the problem is sometimes I agree with your job because the HK stack modified is better, but sometimes you have a noise station or you have a non-homogeneous station. So I think that's it's a difference for the put for the good and the regular station. So you have this HK stacking shows something for us. So it's very important to say that the noise, maybe the noise, if you see the noise stations, okay, because not good correlations, something like that. But for me, it's better to talk about this. Still in this part, you get for six station new for your paper, yeah. So, but about your paper, and the six stations, you got a big difference for VPVS and crustal thickness, and you said that by VP and weight and the HK stack. Do you believe that the weight creates the big difference that both of stations that you show for us in the thesis?
Thank you for the question, George. Really, the difference values adopted as VP of the weights have shows different results, but not as large as we found in the work. So one thing that I mentioned in the thesis is also that in the sections showed appears to be an important sediment layer because the delay of the arrival, that is there is a high influence in the estimation of the crustal thickness. So if we don't correct the sediment layer, we can estimate a thicker crust that really exists in the area. That is one point that I think it's one reason to have a higher crustal thickness compared with the work of Cristobal that processed these two stations. And also, I'm not sure, the work that I read of Cristobal, he processed other time window of data also. And probably the data that I processed is noisier because the available good traces are few comparison with other permanent stations, and it's also a major reason. And in generally, because the location of the stations, the Andes and the Subandean region, are noisy stations by the structure of the area.
It's okay. Let's go to let me see if you have more question about this. I do like talk about for the I really like for our results, but I'd like to talk about for the MERAD and the first figure 3.7 and 3.7 UTs. You show the SVC in the Parapanema province, or Crato, São Francisco Crato, Parapanema, is almost close, yeah. And when you use the lab, why did you use the central station? Because you have nice results, and the Parapanema and the block it's you can show the. Could you show the crustal lab thickness and
Is that right?
yeah, but you have a big the map of Brazil for the lab or no? Did you show?
Yeah. Yeah, of course.
Yeah, yes, it's great, nice. Yeah, you see in the Crato, São Francisco Crato and Paraná block, you can say for these cases it's so crazy idea, but you can say together or not for this case, because it's very, very cool. See this station, this is the lab for this, and you have more discussion MERAD for this. Yeah, here and yeah, you see that. But another problem you see in seismicity, you have so many quake, but the question is, where is the Brazil station, the center of Brazil station? Yeah, it's good.
You mean BDFB, George?
Yeah. You have several results. You reserve several stations in central Brazil. Why you don't use these stations? Because it's a noise, or don't have time for the time of the SP receive push? I don't know. Why don't you use this station in the central Brazil?
Entendeu, Carol?
Entendi. So really, at the first time, we were processing some permanent stations that present good data, and we restricted the evaluation for areas like Borborema province or the Mantiqueira province, and obviously the Paraná, Chaco, and Pantanal basins. And in order to constrain our results, we are opening the area and considering one more station. So when, for example, when we see that this part, this station has a thicker lithosphere, I decided I'm going to process other close station in order to see the patterns. So we are extending to this part. So there are some stations in this part. Really, I didn't process this station until now. I don't know if it has noisy data or no. So I think it's a good point to develop in the future other persons, other work that complete this work of the lab and add more discussion with more data.
Yeah. You know, the Bianchi has some job for these parts. You can use in the BLSP station, that old station. I don't know, it's a good idea, but I think that I have read data or the result of this. I don't know. Eu penso que já tinha alguns resultados aí no Brasil Central feito pelo Bianchi. Eu não sei se...
Sim, ele tem... sorry. Bianchi, in a paper from Heidelberg to 2007, have processed some stations, but there's not really the same station operating right now. So we have processed also some same stations that I didn't talk in the presentation, but I put in the thesis.
Okay.
We have compared mainly these international stations that are SPV and RCB station. The RCB are in the Roraima province, and this station is near to the... Sorry?
Sorocaba, I know.
I don't know the name. It's in the limit of the Parana Basin to the close to the coastal margin. The comparison of results correlates well for stations. It were 4 stations compared. It's not a good quantity of stations. So in general terms, fit well. So that work of Heidelberg of 2007, it was 13 years ago. The amount of data increased too much until now, and there is more and more data to process it. So it could a very, very interesting topic, really. I have many open questions about the LAVs, all the tests really, when we are processing the data and discussing and making the results. Always there is new questions to answer, but it's not possible to answer all questions in one work.
Yeah, I have one or more 2 questions, but the question is for the Província Mantiqueira, still in the lab for this job. You see the 2 stations that in Província Mantiqueira province that has that you show us this station for ON station that show a small peak, and you said that this station for 2 stations Mantiqueira provincia, that the last one and all one, yes, you said it's very close San Francisco crater. And when I see the San Francisco crater for CMC01 and the another one for NBT, it's not so big one. the San Francisco crater, can you show the San Francisco crater? San Francisco crater, yeah. You see the station, it's what the problem for the lab here is. It's a big difference because you said close for this, and the thickness is big than the side of the crater. You have some information, or
so
I don't know.
Okay. I think the first thing is that it's a problem of the color scale. So in the Mantiqueira province, this blue and this light blue is like 110 to 120 kilometers. And in the San Francisco craton, this yellow or orange color is also near to 100 kilometers. I think by the color scale, the difference appears bigger or higher than it really is. But in fact, there is a difference in lithosphere thickness between these stations, closer station or between the San Francisco Craton and Mantiqueira province. Really, I don't know how to explain this difference in geological terms. Also, the S-wave receiver function trace of the stations of Mantiqueira province in this part shows a very weak arrival. So it's very weak, almost invisible, I think. And there was interpreted by considering the noise level or trace, I think could be earlier also the negative arrival.
Yeah, yeah. I believe that maybe, I don't know, of course, I stay with you together, but I really, for me, it's not so clear for both of stations. So you can try, it's very bad. But okay, nice to see about that. The last thing that I would like to say about, you write all the time that South America and the mid plate of South America on the last start regions. It's not true. You wrote 2 times. I'd like to change this because you have some main job in South America, and maybe don't have nice solution, I don't know, but you write for the page 102, begin the mid plate South America. For the interplate, you have a chapter, you have some main paper, you have main years that wrote so much. So you maybe not have so good conclusion. You can compare it by Australia or another place, but you have some job. Please, I just write this and said, please remove that or put another thing. And for the end of the thing that I would like to say, I thank you for the discussion about the MID. It's nice. Thank you for bringing us. It's a nice discussions. You have so many comment, and I just saw just saw the last question for the model 3D model. You get for the 13.6 kilometer. You can see the close of the how to say the criminal oceans and the Brazilian belt, because you have the first result that I see, but you see in the cross thickness, but you can see the picture for the 3 model for the. Could you show the pictures with for cross thickness you get for 3D model?
Slide 42.
Yeah. Let me see. The figure is 48.C. Podia mostrar aquela figura das espessuras crustais feito pelo modelo 3D?
Sim, sorry, I think my connection failed for a bit moment.
International internet, yeah. No, this one.
This, I think.
Yeah. You see the deep 36 kilometers. You have a nice result about I have the paper. There's the name of guys at Tover, and show the exactly close. Maybe Cordani and another people, Tassira, I don't know the name. Showed exactly this close for the Brazilian belt and this part of the craton and another part is excellent result. You do believe that? Do you see this paper? Because you can see it for the Brazilian lineament, but it's very clear for this.
I don't know if I catch it of all the question, but are you talking about that Trans-Brasiliano lineament?
Yeah, I try to explain better because I'm not so clear, of course. So you have a paper, and another guy for Cordani in the Tassida and the Macabira, I don't know the name, but it showed that I have the lineament and it goes north to south in the line, and that say the ocean, the name Crimini, oceans that close and the Brasilia belt for the beating of the Brasilia belt. Okay, it's clear now? No.
Yeah.
Okay.
So you're talking about this part? Hi?
Yes, exactly.
Yeah, really, for the construction of the model, I base it in the available data, mainly from the crustal thickness map presented in the chapter 2. I didn't go deeper about the geological structure in order to understand better any depth of the model. I found interesting patterns also looking the horizontal sections. I really didn't discuss the horizontal sections with the geological settings. So I know a geologist also didn't understand very well these
Okay.
features,
No.
but yeah, the model, if we see any depth profile section, shows interesting patterns that will be good and interesting to discuss with the help of a geologist, I think.
Yeah, I think that's a nice result. I think that's a nice result. And please insert one more example for Amargosa and this paper, if it's possible, not, because it's nice to show two more examples. And and the three models is a nice to put one more example. So for me, it's enough. I'd like to say again, thank you for this thank you for this presentation. It's a nice presentation. Congratulations. It's all. No.
Thank you. Muito obrigada, George.
Very well. Thank you, George, for the contributions and ideas. I make some notes here, and they are all great things that we just let it pass, and for sure we need to review. And then I think if everyone agree, we can move on to Marcelo Assunção. So if you please can share your contributions to us, Marcelo, you are welcome.
Professor Marcelo Bianchi, sorry.
Yeah.
It's possible to do a break of 2 or 3 minutes, please?
Yeah, for me,
Yes,
it's okay.
yes.
Can we do?
Yeah.
Okay,
Sure.
so 3 minutes.
Thank you. I'm back.
Okay, so if everyone is back, we can continue.
Okay.
I think everybody, you can start, Marcelo.
Okay. Well, thanks for inviting me to this thesis presentation. Carolina, I think you did a lot of work. You have very important results. Some of them are really very interesting. But some results still need to be improved, I suppose. I made several notes on the thesis. There are a few typos that you will need to correct. But I would like to start with page 37. You've shown this figure on the when you show all the receiver functions for one station, and then you show another figure with the selected receiver functions. So this has been discussed by Rainer and George. On your thesis, it's figure 2.3. When you choose a few good traces and you do the correlation. So
I think it's also the same figure that I presented here.
Yes, yes. Yes, this one. Yes. So which station is that? Yeah, anyway, so it was not too clear for me how you do the correlation, because you choose one station which has a good receiver function.
I choose a good trace, really.
Yeah, you choose just one, and then you do the correlation with all traces. But even if you use only the PS phase, you still get a move out. So when you do the correlation with all traces, you should need to take into account that different distances will have a different PS time. So how do you use that? So
how we can see in this figure, that this section has don't have the move out correlation yet. So the PS arrival is less affected because it's a lower dipper. Mm-hmm. until 12 seconds. Until that, the effect of the move out is not higher, and we consider a 65% of correlation that allows a window to do a smaller differences of the traces that are not high, because in this section that are all traces at all distances on all move out, the difference of the PS arrival is not higher.
Well, it is not too high. The move out is not too high, but you will have a difference in both in the amplitudes of the direct wave and the PS conversion, and a slight difference in the PS minus P time. So this could, in principle, could affect your correlation. So you could maybe include some traces, or you could exclude some traces that had good receiver functions, but because of this slight move out, did not pass your 65% criteria. I think you are right that you are processing so many stations, and each station has hundreds of receiver functions, that you need a kind of automatic way of selecting the good traces. So this is one possibility, but I think in the future, this needs to be improved. When you compare your results with other published papers, for example, you compare the station TRIB, Trace your mouse. I'm not sure you have this slide.
This is the comparison with...
When you compare the teleseismic stations with the closer deep events. Yes, this one. Yes. So in the left section, when you use only teleseismic events, you just don't see the PS conversion. Right? But there are other papers. For example, we published a paper in 2002 with this same station, and we could see the PS conversion from teleseismic stations. It was a good signal. We even did a waveform modeling for this station, only because we tried different event magnitudes. We used a lower Gauss width filter. So we did like a manual search to get good teleseismic receiver functions. Whereas when you use your automatic procedure, then you're missing the good receiver functions. Okay. So what I mean to say that because you're processing too many stations and too many events, you need an automatic processing. But this automatic processing needs to be improved if you continue to use receiver functions with other stations.
I think I don't know if it's good to call limitation, but the amount of data processed, it was more than 71,000 of receiver function traces in total. It's complicated to do a manual selection because it's a lot of traces. It could take a lot of time also. But I think it's important the suggestion of you, and really if other data with teleseismic data could resolve the crustal thickness or the BPPA ratio with the same method, it's probably that in the automatic selection good traces are discarding. I tried to...
For example, one way is to try slightly different alpha parameter. So, because you're using alpha 5.
Yeah, in the first I was trying 2.5. In some stations there's no difference, and on other stations, mainly noise stations with alpha 5, we can have better results. But it's not since I saw, it's not a bigger difference using these two different alpha parameters. Some stations, mainly the station that has a lower quantity of data, I tried to inspect visually, but these are some, I don't know, maybe 10 stations, but it's a really hard work to do for more than 100 stations in.
Yeah. Yes, one of the things that I was a bit surprised was that your receiver functions for the Peruvian stations are very different from those found by Cristobal Condori. And so this also puzzles me, because we shouldn't get such a large difference in the receiver functions.
Yeah.
So again, I suppose that you are doing this automatic processing, and maybe Cristobal did a manual selection of the larger events or something.
Yeah, it could be, and also Cristobal used a frequency the convolution in the frequency domain. I revised the work of Cristobal, and really the sections are different. So he processed also other window of data, obtained window. So
do you have you didn't show in the presentation, right? A comparison with the Peruvian station? Yes.
So I didn't show in the presentation, but
you have this for this book.
Okay. Sim.
Yes, for example, for this station, Pucon, you're getting the PS conversion from the sediments, right? Which is maybe arrives 1 second later, which is probably expected. And Cristobal, in his receiver functions, the first large peak are all centered around 0. So you see the sediments and he doesn't. So this is a bit strange.
Yeah, I wrote in the thesis, I think that this the effect of the sediment layer tend to estimate a thicker cross that really cross in the area. I didn't correct the sediment effect in the estimation of these stations. And also the data that I received from the Geophysical Institute of Peru, I'm not sure if the data is a quality control really. So I assume that all the data is a good time reference and all things, but the section shows a current delay in the P wave in the P direct arrival. So we are proposing that it's a sediment layer that we didn't take in account in the estimation, and for this reason we are estimating a thicker crust than the work of Cristobal.
Yeah. And also the right-hand seismic section for station San Ignacio Civic. It is very interesting, this pattern between, this is from 100 to 200. These are events from South Sandwich Islands, I suppose. And so you have two big problems here. One is to explain why you don't see the crustal PS conversion at 5 seconds. It just disappeared. And the other problem is to explain why you have a conversion near 10 seconds, near twice as deep. So this is a very interesting problem that will require more work in the future to understand this effect.
Yeah, really, it's an open question for us also, for Bianchi and me, because we observed the section and we don't have any conclusion about the pattern of the section, why the piece is missing in this azimuth. In this azimuth window, it's very clear the station is a good station, other traces are clearer. So I think it's a very good question to resolve in
it's
in the future.
It's subject for a single paper, I suppose. Now, so the crustal section is okay. I don't have more questions, but the lab is a major part of your thesis, and I agree with Rainer that some of the picking of the LAB or MLD is a bit subjective. So can you go back to the LAB session for the craton, for the Amazon craton? By the way, this figure you showed is, in the presentation, it is correct, but in the thesis, it was wrong, right? Okay. So can you show the session? I think slide 27. No, yeah, this one. So I think your results are really nice. You have very good, strong peaks. Some of them near 10 seconds, other near 15, 20 seconds. But your criteria to pick what is the LAB and what is the MLD is kind of subjective. So this makes it difficult to compare with other results. So you could choose the LAB deeper. There are always other peaks coming later than your LAB, and quite often there are other peaks earlier than LAB. So
really, I based it in other works that selecting the first negative arrival as MLD. In these cases where it's
the first or the largest, right?
Also for these traces that presented two negative, are you hearing me? So for the traces that presented two negative arrivals, the first one was interpreting as MLD and the second one as the LIB. So for example, in San Francisco craton, it's very subjective, I agree. The first one could be the MLD, and the second one is very weak, also almost invisible.
Yeah, the second one could be just noise.
Yeah, could be just noise. Could be maybe if the first one is the MLD, the second, the lab could be between 20 and 25 seconds. Is another option. So in this case, we selected the earlier one because to follow the other works, but really could be if the MLD exists and is the first one arrival, a negative arrival, the lab could be between 20 to 25 in these cases. So,
so can you show one section for the Borborema, for example? Yeah, this one. So, for example, for the Borborema, what you are calling the LAB, it could be the MLD. Like the first two stations, you have another peak around 17 seconds, right?
Yeah.
When you say that you only find the MLD in cratonic areas, but this is not quite correct, because you could pick two peaks in several of these other stations in other provinces. But it is clear that this first large peak is on the average arriving earlier than 10 seconds. So it could be in LAB.
Yeah, in the Borborema province, for example, it's more clear than in the Mantiqueira province that there is appears a second arrival between 15 to 20 seconds in this area. I don't know if you are looking my pointer.
Yes, exactly.
In this area. So in order to be consistent with the other closest station, we selected the first one that could be, as we proposed at the final of the chapter, that could be the lab, this first negative arrival, and the lab could be this second and could be disappear in the other traces with the receiver function method. Maybe if the velocity contrast is not too high to be detectable by the method.
So I think your results are very good, but you have some degree of subjectivity in picking some of these LAB, especially in cratonic areas. So you will need to improve this. However, despite this subjectivity, and so maybe some of your picks are not quite correct. Can I share my screen? Can you? Your results agree extremely well with the results of Caio Ciardelli when he estimated the LAB with the surface wave tomography, with the full waveform tomography. So I just want to share my screen. Yeah, so can you see the two maps here? So the left map is from your thesis, and the right-hand map is the result of the LAB from Caio Ciardelli's thesis. He's submitting his thesis next week. And so this is the LAB taken from the steepest negative gradient in the velocity profile. So he has a 3D model for all of South America. For every grid point, he gets the 1D vertical S-wave profile, and he picks the largest negative gradient. Okay, so that would correspond to your largest peak in the S receiver functions. And the agreement is very good. So we have all this area here coming from the Pantanal to southern Brazil with thin lithosphere, which is all these orange stations here. Then we have some thick lithosphere here in the middle of the Paraná Basin, which he also maps here. So he has large lithospheric thickness here in the San Francisco Craton and tending to normal thickness towards the coast, which is what you get here. The Borborema province has a very thin lithosphere, which he also sees here. And here, things are a bit confusing. Overall, your stations in the Amazon Craton tend to show deep lab, whereas his results, some patches you have deep lab, other places you have shallower lab. So maybe like this station, for example, perhaps you're getting what you call the lab, the second weak peak, and he's getting the largest peak, the MLD here. The same thing happens here. Here, these stations indicate deep lab, and he has some of them may be deep and others may be shallow. So here again, it could be that he's taking the highest amplitude, and you're getting the lab, which is not always the highest amplitude of your S receiver functions. But anyway, besides these, despite these problems of picking the first or the second peak, the general agreement is extremely good. And so I should. So I was very, very surprised to see this agreement.
Yeah, I saw the previous version of the results of Caio, but it's not a published work yet, so I can't call in the thesis. So yeah, it's a very, very good agreement. I am so happy also that two different methods converge to the same important characteristics of the parameter. So I agree also with the picking the first or second negative arrival is very subjective. It depends on the interpreter. We tried to be consistent with cluster stations, and mainly if it's a cratonic area, consider the lab could be a higher amplitude, but it's very subjective. If we made an automatic selection that I showed in the correlation, there are different peaks. The automatic selection, we consider the higher arrival between 0 to 20 seconds, and the difference measurements between manual and automatic peaking mainly are in the cratonic areas that present a heat flow lower. So final of the chapter, we question us also if we are resolving the lab or the MLD, or we are mixing these two parameters in web maps. We are in the frontier to distinguish these two discontinuities.
Okay. Can you show you have one of your last slides showing the S wave profile and the effect of temperature. The one that you presented was correct, and the other one, yeah, this one. Can you explain exactly what you mean? When you have a higher heat flow, it should mean that the lab should be shallow, right? Your high heat flow means the asthenosphere is shallower. But here you're only so what exactly do you want to?
Okay, really with we are proposing with areas with higher heat flow, but the lab not necessarily is shallower, but the higher heat flow modifies the velocity structure of all the lithosphere, making that the velocity contrast between the asthenosphere and the lithosphere were not too hard. And that conversion in these areas with higher heat flow is not clearer in the TSE function, or it's absent. So in areas with a lower heat flow, the lithosphere as whole is colder, and the contrast velocity between the asthenosphere and the lithosphere is higher, and it's possible to detect in the S-wave receiver function trace.
Yeah, but then in areas with high heat flow, like in the Borborema, for example, what you are observing then is the MLD, not the LAB, right? Is this what you mean?
Yeah, this means exactly. We are observing maybe the lab, the MLG, sorry, and we are misinterpreting with the lab, because by the area with heat flow, the lab is not don't have a high resolution in the receiver function trace.
Yeah, but then this diagram shows that in areas with low heat flow, like in cratons, right? In Archean cratons, where you expect to have low heat flow, those are the regions where you should expect to detect the lab. This is not exactly what happens, right? Rainer said that there is a question of whether you can really detect lab in all cratons. So this diagram is not too clear for me.
Yeah, we try to explain and figure out our results with this diagram, but the point is that to show is that areas with high heat flow, maybe the lab conversion is not clear in the S-wave receiver function, because the contrast of the velocity in this discontinuity, and in colder areas, this discontinuity could appear even weaker, like in the cratons, and we see in the sections, in some traces the lab appears to be a smaller amplitude. But
yes, but again, see, where does the high heat flow come from? You get high heat flow when the asthenosphere is shallower. Okay? So increasing the temperature does not necessarily decreases the contrast between S-wave velocities between the lithosphere and asthenosphere.
Yeah, but the areas with heat flow, we are proposing that change the velocity structure of the lithosphere as whole, and are hotter, and this heat flow hotter covers the signal in the S-wave receiver function.
Yeah, okay. Anyway, this is something that will need
it's a very big open question, really.
I think it may be a good idea to try to correlate the LAB depth with the Curie depth, because I think heat flow depends on the crustal radiogenic heat production, but it also depends on the lithospheric thickness. So you have two contributions, and the contribution from the crust is sort of constant in the continent, and the Curie depth is a way of inferring variations in temperature. So it might be good to correlate with the Curie temperature. In the thesis, you tested your 3D model. I think your 3D model is a very good contribution to seismicity studies, and it will enable an improvement in earthquake location, especially near the Andes, or even in Brazil. But one of the problems was that you used, well, we still lack a lot of data in the Amazon. For example, you tested with the Guyana earthquake, but you only used stations from the Brazilian network. You should also use stations from, there's one station in Guyana and another station in Venezuela, which are to the east and north of the epicenter. So that will improve the epicenter location.
Yeah, so
and you can test with many other events using peaks from all stations, but not necessarily the ones included in your processing.
Yeah, this is, yeah. The limit of use other stations to the north is that the earthquake epicenter is almost in the limit of the model. So our model is until this latitude.
Ah, okay. So you're just missing.
Yeah.
The station in the French Guiana is just outside your model.
Yeah, for this test, we can use other station to the north. The limitation is the model, not the availability station. But as I mentioned, the way the model is constructed permit to improve even with more accurate P or S wave velocity models, or explain to in area.
Okay, and this 3D model is only for the P waves, right? You're not using S waves.
For now, it's P wave. I tried to construct a S wave counterpart, but it's only using a BPVS ratio for of 1.73. That is a very regional average, and only to try to better constrain the depth or the location. Unfortunately, for the Guyana earthquake, the S-wave arrival and model didn't work well. But in the Amargosa event, I used the S-wave arrival for the closest station, and the location improves a lot. The ellipse of error also, so I only use it one is read, and it's a very average, and this model was constructed with a ratio of 1.73. I think it's important to do a S-wave velocity model considering the sediment layer in the area, and also the crystalline crust ratio corresponding in the different tectonic provinces.
Okay. And can you show again that profile of your model, the east-west profile along 20 degrees latitude? Yeah. So I think you should try to change the color scale for this model, because all the differences, all the main differences, they are just in shades of red, red, dark orange, or it's hard to see. For example, in the crust, there seems to be no difference between the Andean deep crust and the continental crust. Whereas in the stable platform, the average VP is about 6.4. And in the Andes, the average VP is much lower, but we don't see that in this picture.
Yeah, we also consider two different velocity laws for the platform and the Andean region in order to be more correctly with the real velocity of each structure. So I think that in this case, we don't see a contrast, it's a problem of the color scale. I think it's good to maybe prepare other features that shows the different velocity between the platform and the Andean area, because with this scale, it's clear the difference between different structure, sediment layer, the crust, and the mantle, but it's good also to show the different velocities between the Andean and the platform area.
Yes. And there are some papers that show that the eastern Cordillera has average lower velocities in the crust compared to the western. But again, this is not too clear. Maybe it is. It's not too visible in this model. And in this model, you also use the kind of smoothing, right? You don't have large contrasts between crust and model.
Yeah, after the construction of the model using the velocity laws, we are smoothing some points that shows a higher contrast. We have averaged the surrounded points in order to don't have a very high contrast velocity, because it don't represent the realistic area.
But this smoothing, is it necessary for the non-Linlog program to calculate the ray tracing? Is that one of the reasons why you need to do smoothing?
It's not mandatory, but if the contrast of velocity is very high, the program don't converge to a solution.
Mm-hmm. Okay. My final question is one question that George already asked is, you did a lot of work and did a great job with all stations from the Brazilian network, from other temporary networks, but we do have a lot of data from other stations, especially in central Brazil and northern Brazil, that you did not use. Why was that? You did not have time, or you left those other stations for your postdoc?
For the postdoc, is a good is a good answer. As I said many times, that time is a good. It's a constraint to do the things, because I spend more time to processing more stations, or maybe focusing the discussion, or for example, in the lithosphere boundary, the first stations that I processed were from the Amazon region. And the first results, I didn't understand why there was 2 arrivals. And after that, I tried to process more stations with more data. And for example, in the Borborema province, there was another station processed before by Heit et al. And Bianchi, and we moved to the area in order to compare the results that I obtained with other works. And I were opening the study area from these stations. And finally, I didn't plan to process a station from the Amazon part, so I found a thicker lithosphere in the boundary of Pantanal Basin, and I said, I will try another station close. I saw that in the cratonic area, always there were 2 negative arrivals, and I remember that the first time I saw the same thing, and now maybe it could be the MLZ, and I processed one more, but it was in this way. It's not there's not a reason that other station didn't consider it.
Okay.
Like we're opening the study area with that.
Yeah, one good station to compare your processing with those of Heit and others is the Samuel station in Rondônia. That was also processed by Heit. And
I processed it, but I didn't find good results in that station. I processed that station.
Okay. Okay, that's all. I made a few notes on your writing and English mistakes and other things that were not too clear in the thesis, so I'll pass this to you later. Okay. So congratulations on your work. It's a very hard work and very useful results.
Thank you, Professor Marcelo, for your feedback.
Okay. Thank you.
Okay. So thank you, Marcelo, for the points. I think it's really elucidating to see the map of Kyle's together with Carolina results. It really kind of adds a lot of, I think it pushes us to move on into that. And as a advisor, I would just make some points until we finish. First of all, I would like to say that I think some of the things that I heard from all of you, well, all of the contributions were really good. But many of the things kind of push to the main idea. When Carolina starts to work, we really were focused. Like we started from the problem of the Achille earthquake to get a model to relocate, and then like Carolina we move on and said the things and go doing it, starting with the Morro and move on. And then comes the lab, and finally in the last part, it's something that we didn't really kind of publish it yet, is this S receiver functions and the model construction that was done on the last year, mainly like working on that and putting the things together. And I think there is a lot of ambiguity in the picking stuff, and that's kind of, we push it into this automatic procedure of box stacks that was applied in the Paraná Basin. Like, but one thing I would like to ask Carolina is like, do you think it would be possible to do a blind picking of the lab, Carolina? Like, I mean, if I give you traces of stations without knowing which the stations are and where they are, or if I remove the name of the stations, how do you think we could do a blind picking of that?
Really, I think doing a blind picking is not difficult, but I try to pick the largest negative arrival. But for the literature and so in the processing that data, the largest negative arrival could be the MLD.
Yeah.
So if I selecting as MLD where it's an acratonic area, so without the name of the station or the location, I think it's more difficult to constrain the result for MLD or to the lab. We made a blind, like a blind measurements with automatic pick, and the results in the areas like Borborema, the Mantiquera, and some parts of the Paraná and Pantanal Basin converge to the same results. So the problem of the second picking is more in the cratonic and older areas. So
yeah, this is something that we need to think about it, how to do it. It's something that I still have open for myself, how to do it. But listen to the commentaries of Heiner and Marcelo, and also Carlos and George. I was just here sitting and thinking about kind of a blind pick to try to remove this kind of possible influence of the picker somehow, and maybe trying to think about an experiment, like a seismologist experiment to pick this would be interesting. And of course, it's something to improve. Also, well, for me, it's harder to go on because I kind of follow all the work, and I think I participated in the discussions and the evolution of the thing. And I have like one question for you about for me, like I have seen in South America many people moving back on and reprocessing things on a different scale. Like, for example, if you look to partners and Emily's work on Susan Beck's side, they just put together everything that we knew about the Andes to bring a new tomography again. And somehow your work, for me, worked in the same direction. You know, like we step back a little bit, we just maybe move back to the basis and look to the data more deeply, trying to get the best of it. And we are seeing that somehow we are observing new features, like George pointed out, this like a shallow moho that you are showing the map, or other resolution things. But how do you think we can move on and go back and compare again, you know, this kind of more step back results that looks to the whole continental platform, to the local scale studies, like especially in the VPVS? There's a lot of open question in here, and VPVS is one that I would like to point out because there's a lot of individual works that have been done, and we have now this kind of homogenic study of the whole like platform. And how do you think we can move back and learn from this, like, you know, when we look both together? Like, how can we kind of look to your results as a whole platform and compare them to the local results and try to understand the gains? Like, do you have an idea on this that we have been seeing the last years in South America?
Well, yeah, the parameter that you mentioned, the BPVA, it tends to be scattered in general. Compared with other works also, the correlation is not as well as we want, maybe. But I think it's important to back to each work and see how we obtain the results, join the results maybe, or for example, there are stations or areas, and I think that the BPVA is that we have obtained it is most, it's very influenced by sediments and work and compare with other works and try to compilate, as Asunción made for the crustal thickness in 2013 that compiled a lot of works in the area, and the result is a model of all the South American platform. So I think we have to work together with other research. Like now in South America, I think it's a good engranage, but there are parameters of the PBS that are difficult to establish some maybe regional patterns or local patterns because they're very scattered values, and the way to in the P-wave receiver function there varies from 1.8 to 1.6. That is a very huge window, but it's important to review the good stations and compile all the values and study or review the large differences in order to go to a more homogeneous result.
Yeah, I think this is something that I still question myself, but very good. And just to finish, moving back, you know, this picture that Assunção just comments about the shifts in the results that has the heat flow. Yeah, the sketch.
Yeah.
And this is something just to mention. I think this for me comes back to the question, like really, like we have the LAB, and of course it's something that we try to detect as this low velocity stuff, but like this is not really a question to you, but something that maybe for all the members to think, like the idea that maybe we need to understand the whole velocity profile of the crust and not local changes to try to understand this behavior, or having the double or single peaks in the S receiver function, and really trying to map this double or single, it's one starts as Heiner said. So and I think this is the idea here. Maybe the idea of low heat flow and high heat flow would be more interesting to change this to cratonic velocity profile and non-cratonic velocity profile. Would you think that this is more appropriate?
Yeah, so it's appropriate for cratonic and non-cratonic areas, but one thing that I observed that the clarity of the S-wave receiver function depends a lot, of course, of the quantity of data processed. So, for example, in the Paraná Basin, Chaco Basin, there is a lot of temporary stations, so the number of data is not so high, and the traces are so noisy. There are negative variables that is in the noise level, and it's difficult to pick and make conclusions about traces. I think it's important to collect more data. It's a first step, I think. The first time that I processed the LIB was 2 years ago, and in the final of the last year, I reprocessed it with more data, and I saw a very high improves.
Okay, yeah, really. Yeah, it was really good. I have seen the initial results, and this one they do change. But I think that's it. I think some points that I would just like to bring to the overall discussion. I was very happy with all the results in the end, all the discussions and the final. So I would like to congratulate you and thank you all the members for the contributions. So now I think we should kind of finish this set of questions. And if I'm not forgetting anything, I think we need now to join ourselves to make the final decision in a private room, I think. Yeah, so I don't know if Alexandre, can you help us? Alexandre, você pode ajudar a gente? Como é que funciona? Okay. Okay, Carolina, I think we're going to leave the session here for a private room, and we're going to go to the final decisions. Does anyone wants to make any final comments before we move into this other room, or should we go there? Ok. Isso, são os dois Marcelos, o Rainer, o Carlos e o Jorge. Yeah, now all the members should click.
Não, não consegui. Não sei por que não está aparecendo aqui. Deixa eu ver aqui. Não consegui ainda. Poxa, por que não? Vai me levar para lá? Não sei por que não estou conseguindo entrar. Nada? Vou fazer o seguinte, vou sair e vou voltar de novo, tá? Deixa eu fazer aqui. Aparece a sala aqui, mas não aparece para entrar. Eu vou entrar pelo celular, porque está muito esquisito. Uhum.
George, talvez você desativou os pop-ups, porque aparece um pop-up para você aceitar o convite.
Ah, tá, deixa eu ver aqui. Não, os pop-up estão ativados, apareceu aqui, mas eu não consigo clicar em cima dele, não sei por quê. Você botou jorgefranca@gmail.com? Não, bota jorgefranca@gmail. Me dá Ah, não dá por aqui. Marcelo tá ligando aqui. Estou tentando entrar aqui, Marcelo, mas não está conseguindo não. Não sei o que aqui é não. Aparece, mas não tem nada para clicar, entendeu? Estou só esperando aqui, estou esperando ver aqui com o Alexandre. Vou mandar mensagem lá para o Bianchi, e aqui eu não consegui entrar para ver se ele manda o link para mim. Não sei por quê.
Até para mim apareceu um pop-up
Então,
para, tipo, aceitar, recusar. Eu recusei, né?
O meu aqui está tudo permitido, não tem nada fechado, eu não sei o que
Você
é.
está no Chrome ou está no Firefox?
Eu estou no Chrome.
Ah, tá, porque o Chrome é mais fácil de lidar. O Firefox, ele não permite abrir as janelas.
Ah, ele está dizendo aqui que tem algum problema na rede, não sei se é. Ele está me falando aqui um errozinho, mas não são os problemas, sei lá. Estranho, gente. O pessoal não quer que eu ative ali, não, Carol.
Não, por Deus. Acho que se o Bianchi te enviou o link, aí você pode aceitar. Eu acho, não tenho certeza.
É porque dessa reunião é aqui mesmo. Nossa, anexo, não estou vendo, mas... Não tem onde clicar. Vou fechar meu microfone aqui, vou falar com ele.
¿Consiguió now, George? Putz.
Tá mutado, seu.
Ah, agora foi. We are all back.
Yeah, I'm back.
Very good. So we are all back here, Carolina, to give you the results. So all the members approved your work, so you are approved and can work even harder to finish the work and all the papers that are still promised and discussed. We have a lot to do still. I hope we can continue and, of course, bring all the collaborations that we can from the members and the ideas from Carlos. For sure, we're going to contact you again. So congratulations, Carolina.
Thank you to everyone. I would like to thank firstly my advisor for the patents, the friendship, the supporting all this time, the members of the Seismological Center of the University of Sao Paulo, the Institute of Astronomy, Geophysics, and Atmospheric Science. Thanks, everyone. Thank you, Shun, Kim. Thanks for the comments. It's a very important feedback for us to better the discussion and finish the work and make our conclusions of all the results obtained. Thank you, everyone.
Very good. So I think we succeeded, and thank you again, all of you. Alexandre, você tá por aí, Ale? Tá, eu acho que a gente pode terminar já ou não? I think we can finish now.
Okay.